Hello, everyone, and welcome to the Daily Space for today, November 15th, 2019. I've been away this week traveling out to the QCon conference out in San Francisco, California. And I have to start by thanking Susie and Annie for everything they did to keep everything going while I was away. And I'd also like to thank everyone at QCon for creating such an inspiring environment that really makes me wish that I hadn't had to spend so much time working on grant writing. But hey, I got a grant submitted today. It's been a week, people. It's been a week. And now I'm going to do catch up on everything else. And then it's going to be coding all the way down. And you're going to be invited to join me. So expect random ninja streams starting as soon as I've caught up on my inbox. And we're going to be working on making our home here on CosmoQuest a little more comfortable. Now, news, there's news. I'm going to keep it short and simple because the three stories I'm going to start with today are ones that are weird and they're cool and they're confusing. So I think three weird, cool, confusing stories is enough for any one given day. So in our first story of confusing and awesome, I have a story about how the structure of our universe influences the way that objects spin. Galaxies form, as near as we can tell, in two different ways. The first is they formed early on in the universe in this massive inflow of material that, thanks to chaotic turbulent flows, was able to spin up a massive black hole, create a massive galaxy all at the same time. This is amazing. That's a word I'm going to use a lot today. But it's rare. The majority of galaxies that we see out across our universe are actually formed through a smaller bottom-up approach, where what happens instead is you get this little cloud of material, spins up, materializes, shines with stars. You get another one over here. Over time, these two come together. If their angular momentum is just right, they form a beautiful spiral galaxy. And through this slow influx of small systems into bigger and bigger systems, we're able to build galaxies. Now, if you do, as a bunch of astronomers did using a telescope down in Australia, if you look at a whole lot of galaxies and compare how they're rotating to where they're located relative to the large filaments that really define the structure of our universe, what they find is that small systems tend to spin, well, in one alignment relative to those filaments, whereas as they get in, they will flip 90 degrees with the bigger galaxies that have undergone all sorts of traumatic rotations, flipping in a perpendicular orientation. And the way they explain this is it's like two people roller skating. If you're both trying to plug along in the same direction, as you grab hands, you're going to rotate 90 degrees. And this flip can be sudden. Now, this is the kind of research that makes me want to dig in and look at their statistics and see how does this work when you start looking at systems that are more isolated. How does the inflow into a system torque it into one orientation, and then collisions once it's inside that system trigger the alignment change? There's a lot of physics to dig into, but this is an observational result, which means that within the systems they looked at, this is what our reality is doing. And this is the kind of thing I for one, wouldn't have foreseen as so cut and dried. And it's awesome when the universe surprises us with something that appears to be such a neat and clean result. So cool. There is a systematic alignment of small and large galaxies with the filaments that make up the large-scale structure of our universe. And that's just cool. that's just cool. That's all I've got. Now, in more news of things that align with one another, these are two different star-forming regions. One is in the Large Magellanic Cloud, the other is in the Small Magellanic Cloud. And what is really weird about these two systems is they look very, very similar. They're the exact same age, and they're 150 light years apart. Now, the way this is getting understood is that these two clouds of material in the Large and Small Magellanic Cloud actually interacted with each other at some point in the past, and they're thinking that point was 200 million years ago, when the Large and Small Magellanic Cloud had a violent gravitational interaction. And it was this interaction that triggered the star formation that we're seeing here. They are saying that these two things look like peacock tails, and I'm going to agree with that, but I'm also going to point out this is data from the Atacama Large Millimeter Array, which means that some scientists picked those colors. And each color represents a different wavelength of light, but it's light that our eyeballs couldn't normally see. So this is more representative color where we've shifted everything into what our eyeballs can deal with and picked colors that made it look like a peacock along the way because we can. Now, I, for one, had never really thought about the Large and Small Magellanic Clouds violently affecting one another. I just had always thought that our Milky Way right here is the dominant thing triggering, well, the star formation and other interactions that we see going on in these systems. But we have to think longer term than what we see in the sky right now. And over the course of the history of these systems and our system, there was that interaction 200 million years ago. And in trying to understand everything that we see, we need to include that in our models. And that allows us to understand what we're seeing here. It's one of those days of everything interacting with everything. And our final story is yet another one of these everything interacting with everything kind of stories. And here too, in the moons of Neptune, this is leading to cool alignments. What we are seeing here, and I have to look at my notes, what we are seeing here is the dance of two different of Neptune's moons. This is Naiad and Thalassia, or Thalassa. These two moons are located about the same distance from Neptune, on orbits that are just slightly tilted relative to one another. And this somewhat confusing graphic, what it's showing is what you would see if you were constantly straight over the moon Thalassa as it went round and round Neptune, and as it watched its fellow moon Naiad go round and round. Now, Naiad is orbiting every 7.5 hours, whereas Thalassa is orbiting every 7 hours. And this resonance is causing Thalassa to see Naiad go beneath it twice, over it twice, beneath it twice, over it twice, in this lockstep resonance. The difference in their orbits is very small. The tilt difference is just enough to mean that these two objects can cross the same places in space over and over, but never do it at the same time. This is a really cool dance where two objects have found a way to coexist, do it stably, and do it in a way that produces really pretty and also really confusing data visualizations. This is the kind of thing that you should, in theory, be able to figure out how to do in Universe in a Sandbox or Stellarium. I'm just going to show you the graphic that NASA has shared with us. And that's all I've got for today, because I know these are the kinds of stories that are going to generate a whole lot of questions. So I'm going to encourage you to go ahead and type those questions in now. And while you do it, I'm going to remind you that my name is Pamela Gay, And I am part of the team that brings you the Daily Space. We're a production of the Planetary Science Institute, and we are produced by Susie Murph. We are brought to you by you. It is your bits, your subs, your patronage over at patreon.com/CosmoQuestX that allows us to pay our bills. During the month of November, we are running a fundraiser that is not currently up on screen. We are, during the month of November, running a fundraiser where we are trying to raise money to pay for our servers in 2020. We use Amazon Web Services to host all of our different stuff and things. This means that if a machine breaks, we don't have to pay to replace it, but we do essentially have to rent our systems. We want to pay for everything, which will get us a substantial discount in costs. And we can only do this with your help. So if you want to help us make sure that our website and our archives and our RSS and all these things we keep on the internet keeps on having a place to be kept on the internet, please consider giving. We are using a Streamlabs link, streamlabs.com/CosmoQuestX. And the reason that we're doing that is because the Planetary Science Institute is a 501c3. By donating through that PayPal link at Streamlabs, your donations will be tax deductible wherever allowed by law. So if you can help us keep our servers, you will make me a very happy person. And that's all I've got. I hate begging for money. Thank you. I'm now going to say what questions you have. I'm laughing at Nightbot showing so much love for Astro B London. So Raj is commenting that NASA or another space agency should seriously send a spacecraft to Neptune or Uranus. Yes, all the scientists, not all, a lot of us scientists have been saying the same thing. The problem is that they're so far away that you either have to have a huge velocity and then massively change the direction of that velocity when you get to the world to get there at a reasonable time scale, or you have to wait like a generation of scientists for your more reasonably paced spacecraft to make it that far through space. Thank you so much for the bits. Eddie, come around to the other. No, you're on the wrong side, dude. Okay, you can have it on that side. That is fine. There is the saddest, cutest dog head on my desk right now. Hi, you want this? Come here. You're good. You're going to drool on me, aren't you? Thank you so much, Broken Symmetry and Checker Kev, for the bits. Thank you. Here you go. You're so good. So good. He's my bestest boy. I kind of adore him. Okay, so yes, we know we need to send a spacecraft to Uranus or Neptune. The Delta V is kind of killer. Okay, I'm just going to scroll up to the top. I'm going to say thank you, Wicked Wonder, for your tier 1 sub for 3 months that you did before our show got started. Good evening, Guido. Good evening, K. Barat. Hello, the art of DHT. Hello, Broken Symmetry. Hello, Mike Cassidy. Hello, Michael Mayer. Hello, Ironheart. Hello, Mythtown. Hello, Wayne Johnson. I just have to say it that way because your name's in all caps. Hello, Fenring. Hello, Raj Luthra. Hello, Larry. Hello, DPI 209. Scrolling for questions. Scrolling for questions. Hello, Astro B London. So Fenring asks, how likely is that moon dance to happen? Have we ever found something similar, or is this considered rare? So we find things in resonances all the time. This particular resonance, I don't know of another example of, but that could simply be lack of my knowledge. Thank you for, what was that? Thank you, Mythtown, for gifting subs. That is amazing. Wait, here you go. Hi, hi, hi. Hi, you're moving my desk. You're really moving my desk. Come here. There we go. So one of the reasons I just don't know how common it is there's so many moons around Saturn and Jupiter that I don't know if any of them do this, but I haven't seen a press release of any of them doing it. It seems like the kind of thing someone would have written a press release about. Now, what I do know is the Galilean moons of Jupiter are also in a really cool resonance where they basically go around in interval numbers of each other. So this is Io, Callista, Ganymede, and Europa. I don't quite remember what order they're in. I think Io is the one that's closest in. And they go around so that one will go around once, the other will go around twice, and it's the innermost one that goes around the fastest. And this going from being all lined up to 1 and 3 and all the other different intervals is what is able to heat Io to cause all of the volcanism that we see and heat Europa for all of the geysers and potential of an under ice ocean that we see. So resonances like this can be super cool, and we do see other resonances. I just don't know if we see anything else quite like this. There's also a bunch of asteroids that are in resonances with Jupiter going around the sun. So the question is, do we still think that Neptune has diamond moons? And that comes from Larry. Not moons, diamond mountains. English is hard. English is very hard, people. Thank you for the donation. I can't see who that is, but it rounded us all the way up to $1,000, and that's awesome. Someone mathed. And I'm going to find the correct window so that I can... Hi. You guys can't appreciate how much he just moved the desk. Show me what's happening on the stream, you silly thing. Oh, they rearranged the interface on Twitch while I was traveling. Can't find things now. It's all right. You can watch the dog goober all over my hand while I figure this out. Thank you so much. Hi. Are you having a good lick? You are. For those of you who don't know him, this is Eddie. He is my bestest boy. Thank you, Michael Mayer. Thank you so much. Thank you. Our servers will be happier. Okay, so going back to questions. Count your fingers. My dog's really good about only goobering me, so I may end up with a gross hand, but I will keep everything intact. They're also soft-palated, so even if they do chomp, it's not as bad as it could be with other kinds of dogs. Your bestest boy was barking because they saw your pooch. I'm sorry, Mythtown, but I'm really not sorry. So Kerbal, we brought up the star that was ejected by Sag A star yesterday. For those of you who don't know the story, a star was found on an amazingly rapid velocity trajectory that has it heading out of our galaxy. And when you see something moving in one direction, you can work backwards to figure out where it came from. It's a little complicated because you have to take into account how everything in our galaxy is moving in three-dimensional space. But when they ran these motions backwards, they figured out it had originated in the center of our galaxy. And this can be explained by a binary system falling in towards the central supermassive black hole. And the central supermassive black hole's gravity and the three-body interaction that comes of this can yank apart the binary system, keep one of the binaries in a close orbit, and send the other one flying out of our galaxy. This particular star is going to leave the Milky Way in about 100 million years, which is the blink of an eye in our galaxy. It takes us over 200 million years just to orbit the galaxy. What other questions do we have? I think I missed in the scrolling. Did I miss anything? No, I think I got everything. Okay, so I am back. I am here, home again. For those of you who weren't here earlier, I just want to give a shout out to Susie and Annie and all the mods for keeping everything running while I was traveling this week. I had an amazing experience at QCon. I'm so grateful to the organizers for giving me that opportunity. And things are going well. Today we got a grant submitted to the National Science Foundation. We currently have 3 different grants pending that will fund our citizen science activities and research related to the citizen science. So thank you for your bits and subs are what keep us going and allow us to open doors for ourselves. So you're essentially unlocking the doors that we then get to open. That was a really bad analogy. I need more coffee. Later today, we will be doing a live recording of Astronomy Cast. It will be co-streamed right here on twitch.tv. That starts in just over an hour and a half. I'm going to now go grab some lunch and prep for my next show. We are also going to be working, now that I'm home, to start prepping for the Hangout-a-thon this year. If you want to be part, join us over on Discord. Help us know what you want to see for our 40 hours of straight streaming during our December fundraising telethon that's here, so we call it a Hangout-a-thon. That's all I've got. You are wonderful. I'm now going to say this has been a production of the Planetary Science Institute. We are produced by Susie Murph. We come to you most Mondays through Fridays live on twitch.tv/CosmoQuestX at 10 a.m. Pacific, 1 p.m. Eastern, and that is 6 p.m. London time. We are here because of you. We are sustained through your bits, your subs, your donations over at patreon.com/CosmoQuestX. If you like what you see, consider joining us over on Patreon. It is a way that we can get you even more content. So thank you. And wherever you are in the world, have a fabulous morning, evening, or afternoon. And I'll see you on the other side.